So, to graph these rather complex trigonometric functions, you will need to understand how to use the period, how to find the associated asymptotes, and then you will be able to spot the points that will be helpful when trying to determine where the functions are defined and undefined. So in this case, in the first trigonometric function, as you can see, we're going to start working with the parent tangent function. So the first thing that you want to do, you want to find an angle at which this tangent function is undefined. Okay, so we know that tangent of pi over 2, well, let's start with the negative. Negative pi over 2 is undefined, right? We know that, right? So I'm going to say undefined, right? Because the sine of negative pi over 2 is negative 1, but the cosine of negative pi over 2 is 0, right? Sine divided by the cosine is the tangent. 1 divided by 0 is undefined. You cannot divide by 0. Thus, the tangent of negative pi over 2 is undefined. So we already found basically an asymptotic x value, but we have to plug this negative pi over 2 in such a way that it's equal to the overall angle for this function, right? Because it's revised. As you can see, it's not just the t, it's also 1/2 times the t. So to find the t value respective to this particular tangent function, we have to set 1/2 t to the problematic x value that gave us an asymptotic line for the tangent. So as a result, if you solve for t, multiplying both sides by 2 will yield you t is equal to negative pi, right? Because the 2's will cancel out. So now the period, as you know, the period formula is going to be the pi, because this is the normal period for the tangent function, tan of t. So pi will be divided by this 1/2, as you know, right? This is the b value in the standard equation, a tan bt minus c plus d, right? You remember that. So b is the 1/2 value, so you divide pi by b to give you the period, and that way it's going to be 2 pi. Right? So this makes sense, right? Because as you can see, if you plug in the next problematic asymptotic line, or the t value for the parent function for the tan, you will get pi over 2, right? Tan of pi over 2 is also undefined. If you plug in pi over 2 here, the t would be pi, right? And that makes sense, because if you add 2 pi, the complete period for this tangent function, guess what happens? You would get exactly pi, the next problematic t value for the asymptote at which this tangent function will not be defined. Right? So let's plug these in. So negative pi, I'm going to put it here, negative pi, and I'm going to put pi here. And if you plug in t value of 0, tangent of 0 is 0, right? Because sine of 0 is 0, cosine of 0 is 1. Therefore, 0 divided by 1 is 0. So we can confidently put this point here. Now, as you know, we can also mark the asymptotic lines that we just found for the t values, negative pi and pi. Okay, this will be the asymptotes. So as you might have guessed, graphically, you don't even have to do algebraic work anymore, because you know for every multiple of 2 pi, the absolute value distance between the asymptotes is 2 pi. You just add that to the next asymptote value, and then you get the one after that, right? So pi plus 2 pi is 3 pi, right? So we know this is going to be the next asymptotic line for this particular tangent function. And we can mark it as 3 pi, all right? And the same thing on the left side. Subtract 2 pi basically from this one, you will get minus 3 pi, right? This is minus 2 pi, this is minus 3 pi, right? So this is going to be the next asymptotic line on the left side. Again, we can mark it as minus 3 pi. Okay. So now, as you know, since the coefficient of this tangent function is positive 1, it's going to be rising from left to right, right? So basically, it's going to fall from right to left, and it's going to rise from left to right, right? So it's going to behave something like this. And if you want to confirm that, plug in the negative pi over 2 into this function, you will get negative pi over 4 for the tangent. right? Let's just play around with it. Tangent of, plug in negative pi over 2, which is right in the middle between 0 and negative pi. This is negative pi over 2, right? If you plug this in, you will get tangent of negative pi over 4. Now recall that when tangent is negative pi over 4, you're talking about negative tan of pi over 4 because this is an odd function. Tangent is an odd function, thus the negative inside can be carried out and then the input becomes positive, right? That's only because this is an odd function. And notice that it makes sense because odd functions are symmetric with respect to the origin. As you can see, there's symmetry with respect to the origin here. Not u-axis symmetry, not t-axis symmetry, but the origin symmetry, right? So that makes sense. So minus tan of pi over 4. Now, as you know, minus tan over pi over 4 is going to be minus sine of pi over 4 divided by minus cosine of pi over 4. Not minus, just plus. Just plus cosine of pi over 4 because we already have one negative outside. That's it. So that's going to give us what? We know that the sine of pi over 4 and cosine of pi over 4 are both radical 2 over 2, the same value, right? So it's essentially going to be 1 plus that negative there. Don't forget the negative, you will have negative 1. Does that make sense with what we have here? Well, let's see. It does, right? Because if you plug in negative 1 here, if you let this be negative 1 and this be negative 2, etc., notice that negative 1 is definitely lower than 0, right? So our initial understanding of this tangent function behaving this way, rising from left to right or increasing function from left to right, it was actually correct, right? So the tangent of the input for the t-value of negative pi over 2 gives you negative 1, right? Smaller than the value of 0 at the t-value of 0, right? And confirmed algebraically, just for your own practice, if you plug in pi over 2 for the t-value here, you will see you will have tangent of pi over 4. And tangent of pi over 4 is 1, right? So if you let this be equal to 1, I know that it's not a perfect drawing, it doesn't touch 1 exactly, but what's correct is that it definitely rises, right? The value of pi over 4 here, pi over 2 here is definitely higher than the value of 0, right? The value at t is equal to 0 is 0. The value at t is equal to pi over 2 is 1, right? So it's definitely higher. So the understanding that the tangent function is increasing from left to right is absolutely correct. And that's only true if there's a positive coefficient. If there were a negative coefficient for the tan, in negative tan, for example, it would be switched around, right? It would fall from left to right. It would look something like this, okay? If it were minus tan, but there's a positive coefficient, so it's the way it is that we drew. Okay, we have to draw the other. Notice the tangent functions repeat themselves, right? This is the complete cycle. So we know even without confirmation that the next 0 is going to be here, and then it's going to be rising from left to right again like this in the same fashion, right? So it kind of copies itself, right? Like the tangent, like the cosine and sine, except it's not continuous everywhere, right? There's no continuity at these asymptotic problematic t values, right? Pi, 3 pi, negative 3 pi. But however, you see the copies are still being made. The next 0 is going to be here, right? At negative 2 pi. You go here, you rise, you fall from right to left, you rise from left to right, right? And the same thing there, and the same thing here. Okay? So this is how you would graph the tangent of 1/2 of t. And if you want to confirm, just for your own practice, plug in negative 2 pi here for the t value, you will see you will get a 0, right? Because negative 2 pi cancels out with a 2, it gives you minus pi. Tan of minus pi is the same thing minus tan of pi because it's an odd function. Tan of pi is 0. Minus 0 is still 0, right? So it makes sense. And also you can plug in the 2 pi here. It will give you the same result. Plug in the t value of 2 pi, you will get a 0. And if you want for fun, plug in these values, you will see you will get higher. Plug in this value, that will be what? Pi over 2, 3 pi over 2, right? 3 pi over 2. Plug in, you will see it will give you a negative value. Right? So this is just for your own practice, but I showed you basically a shortcut to graphing this correctly without any mistakes. Now, the next one is going to be minus secant of 2t. Now, minus secant of 2t. First of all, let's take a look at the secant, the regular secant that we know. The secant of t function. So we know secant is going to be 1 over cosine of t. Now, as you can tell, when cosine is equal to 0, there's a t value that will give you a cosine of 0, secant will be undefined, right? So now we know cosine of negative pi over 2 is 0. Cosine of pi over 2 is 0, right? So you know the values that you will set 2t equal to, right? You will not plug them in as the t, but you will set 2t equal to negative pi over 2, because you know these are the problematic angle measures for the parent secant function, for the t value for the parent secant function, right? So you want to find what the actual angle for this revised secant is, right? Because revised, I mean because there's a 2 there, right? It's not a coefficient of 1 that you've used to see, right? It's the 2 now. It makes the period twice as short right now. Before, for the tangent function, the period was twice as long because of that 1/2. Now the period is twice as short. So how do we find the period? So the regular period, as you can tell, is the difference between these two problematic t values for the regular secant function. And that's going to be pi, right? That's going to be the distance from pi over 2 to negative pi over 2, right? The absolute distance is pi. So that means we take pi, because that's the regular period for the secant, and divide it by the b value, which is 2. So as you can see, what I said is absolutely correct, because the period now is twice as short as it used to be. Right? For this one, the period was pi. For this one, because of that 2, we divided by that b value, we get it, right? It's pi over 2 now, the period. So now let's find a problematic asymptotic line from which we will add the period, and we will get the next asymptotic line, right? The same way we did the tangent. So that means we will do what? We will do minus pi over 2. We will set that problematic angle to this complete angle 2t, and then solve for t. Dividing both sides by 2 will give us t is equal to negative pi over 4. Bingo. We just found an asymptotic line. Now let's find another one. Negative pi over 4 plus the period, plus the complete cycle, right? The length that it takes a complete cycle for the secant function here is going to be plus pi over 2. Right, plus the period will give us another value. And minus pi over 4 plus pi over 2 is pi over 4. And as you can see, this pi over 4 will be confirmed if you plug in this value. If you set this value, pi over 2 equal to 2t, the same thing we did for the minus pi over 2, we set this pi over 2 to t. T, dividing both sides by 2, will give you pi over 4. Exactly what we thought, right? So two ways of finding another asymptote, right? Just adding the period to the previous asymptotic line, which we would get another asymptotic line, or plugging in another problematic value for the secant, for the original secant, the parent secant, and then simply setting it equal to 2t, right? And finding it that way. So two ways of doing it, and both ways work, right? So in other words, we found the problematic asymptotic lines, this one and that one, for this secant function, for the revised secant function that has a 2 there now. All right, so let's do that. So t is minus pi over 4. So how do you want to graph this? I want to mark this as minus pi over 4. Okay, and I want to mark this as pi over 4, and all the multiples of pi over 4, right? So the next one will be, let's see, adding another pi over 2. That's going to be here, right? Pi over 4 plus pi over 2. Let's see, 2 pi's over 4 will give you pi over 2, right? So 3 pi over 4. This must be 3 pi over 4. And this must be, let's add 2 more ticks. That would give us minus 2, minus 3, right? So minus 3 pi over 4 is going to be here, right? So let's mark them as asymptotes, and let's see what's going on after that. So, so these are the asymptotic lines for the secant of 2t. So let's see. So these are the asymptotes at which the secant function given on the top is not defined. Okay. And let's keep going. Let's add one more here. And let's add the remaining one right here. Okay, so now how do we actually graph it? Now that we have the asymptotes, we know basically where the secant of 2t is going to be filled in, right? But there's also a minus. So let's go by the trial and error. We know that the secant lowest point, or the highest point, depending where you are in one of these chunks here between the asymptotes, will touch the cosine friendly function that it depends on, right? Because one is the reciprocal of the other, right? So we know where the cosine is the highest will be the lowest point for the secant. Whenever the cosine is the lowest point will be the highest point for the secant, right? So that's a beautiful thing about it. So, but we can also plug in the t value. When when t is equal to 0, the u value, the t value is 0. What is the u going to be? What is the function value going to be? Let's see. Secant of 0 is going to be 1 over cosine of 0. Cosine of 0 is 1. 1 over 1 is 1, right? But there's a negative, right? So there's going to be a negative 1, right? So when t value is 0, secant of 0 is 1, but there's a negative, so we get negative 1 right there. Okay? Now we know the cosine, this thing is going to be negative 1 over cosine, right? So let's understand that. Negative secant of 2t is going to be minus 1 over cosine of 2t. Be sure you understand that. Okay? So, and we know cosine of 2t, the highest point is still going to be 1 or negative 1, right? Because the coefficient is 1. Right? So the highest point is 1. The amplitude is going to be 1 for the cosine, right? And that confirms the fact that there's a negative 1 that's going to be the lowest point for the cosine and the highest point for the secant function, right? So that means we're actually going like this. Going like this. Okay? Now also, the next one, let's see. So the next one, we know the cosine. We know the cosine of 2 pi over 4 or pi over 2. Let me write it this way. Pi over 2. This is minus pi over 2, right? We know that. So cosine of pi over 2. If you plug in pi over 2 here, you will get cosine of pi. Cosine of pi is minus 1, right? Cosine of pi is minus 1. Together with that minus 1 on the top will give you 1. Right, so it makes sense now that for this chunk, the lowest point, the highest point is going to be for the cosine, and it's going to be the lowest point for the secant function, for the minus secant of 2t. Right, so it's going to be the lowest point. For the cosine will be 1, like it was the lowest point for the cosine, but it will be the lowest point for the secant, for the minus secant of 2t, right? It's going to rise from there, from then on. So we know that it's going to be 1. And it's going to rise like this on both sides. Now, how can we confirm that? If you plug in pi over 2 here, you will get secant of pi. Secant of pi is going to be 1 over negative 1, which is basically negative 1. The negating negative 1 gives you positive 1. Bingo. There you go. Right? So that's the lowest point. Now, how do I know that this is the lowest point, though? How do I know this is the lowest point? Well, I know it's the lowest point because if you plug in a value of, let's see, pi over 8. So this is 3 pi over 8, okay? Just plug in for your own practice 3 pi over 8, the value right between pi over 4 and pi over 2. You will see that the secant will be greater than 1. Let's see, I'm just gonna write this out. So cosine negative 1 over cosine of 2 times 3 pi over 8. I'm just checking this to let you know that it actually works. Negative 1 over cosine of, this cancels out, this becomes a 4. So 3 pi over 4. That gives me negative 1 over radical 2 over 2. We know that. The cosine of 3 pi over 4 is radical 2 over 2. So that becomes minus 2 over radical 2, which is minus radical 2. Now if you check in your calculator for the minus radical 2, oh, I'm sorry, this should be a minus sign, minus, and this should be a plus, right? So that would be a plus. Right, so the cosine of minus radical 2 over, the cosine of 3 pi over 4 is negative, minus radical 2 over 2, right? That's a minus. So this is a minus. So together with two minuses give you a plus, right? So it's going to be just radical 2. If you check your calculator, radical 2 gives you 1.41. And as you can see, 1.41 is definitely greater, right here, right? It's not exactly, doesn't align very well with the number system here, but you can see it's definitely greater than 1, right? So 3 pi over 8 for the t value being plugged in here for the secant, and you know the secant is negative 1 over cosine, right? Negative secant is negative 1 over cosine. You will definitely get a higher value than 1. And the same thing here. This point would be what? 3 pi over 8. 5 pi over 8, right? 5 pi over 8. If you plug this into your calculator and making sure that you're in the radian mode, do it like this and then plug it in your calculator. Let's say negative 1 over cosine twice 5 pi over 8 and solve it nicely, making sure that you follow the signs, you will get a positive value as well, right? You will also get radical 2 plus radical 2, right? So you will confirm that indeed this is the lowest point for the secant. So also you can tell that it alternates, right? It goes below the t-axis, above the t-axis per each chunk of space between the asymptotes, right? So the next one with the lowest value of 1 for the secant will be this one, right? And then we don't have space to show the ones with the highest value, but you see where this is getting at, right? The next chunk will look like this. The next chunk here will look like this as well. And when I said it has a great relationship with the cosine highest point being the secant lowest point, it's absolutely correct, right? Because we know that we can connect these points together. And as you can see, usually the cosine, its friend, starts from the top, right? The highest value of 1. But there's a negative, and negative reflects over the t-axis. That's why the cosine, negative cosine of 2t, if you were to just write minus cosine of 2t, the friendly function of the minus secant of 2t, you will see when you plug in 0, cosine of 0 is 1, but there's a minus. So it confirms this point for the negative cosine of 2t, being negative 1. For the 0 value of t. Okay? So it definitely rises. And as you can see, the pi over 4 will give you 0 for the cosine if you were to plot it, right? The pi over 4, if you plug in here, you will get pi over 2. Cosine of pi over 2 is 0. Minus or plus doesn't matter, right? So it's definitely going to be like this. And negative pi over 4 will give you the same result, and negative 3 pi over 4 will give you the same result, and 3 pi over 4 will give you the same 0 result for this negative cosine of 2t, right? So if you were to connect it, it would look like this. So as you can see, it does have a very nice relationship with the cosine function, right? No wonder it's a reciprocal. It's not just a reciprocal, it has this kind of graphical relationship with the secant function. The only being difference here that there's a negation, right? There's a reflection through the t-axis of a normal secant with a positive coefficient that you're accustomed to see. That's why the cosine at 0 is negative 1 and not positive 1. And it pretty much looks like sine function almost, except it's moved pi over 4 units to the left, right? Imagine a sine function being moved pi over 4 units to the left. Okay, so this is basically the relationship that you should be able to understand. So I'm going to mark this as minus cosine of 2t, just so that you have an idea. And this is going to be negative secant of 2t, right, for the blue ones that we've drawn. And this, of course, was the tangent of 1/2 t. So I hope this was useful. Thanks so much for your patience in watching this, and I'll see you in the next video.